Good. So what I did in this chapter so far, I taught flip-flops, okay? And then I told you any sequential circuit must have flip-flops. Is that okay? It may have combinational circuit or not, but at least it must have flip-flops. You got what I'm saying? To create sequential circuit. And then here in this chapter, in the analysis of sequential circuits, clocked or synchronized is the same thing. That means we achieve synchronization through clock. So, and that's exactly what we do. What we do is we connect all the circuit using the same clock, and the objective of this clock is to achieve synchronization, as I said before. Here I explain, in case of combinational circuit, if I want to describe the behavior of the circuit, in other words, if I want to know how the circuit works, what is the relation between input and output, we use the truth table. But here, in case of sequential, we are not going to make truth table. Instead, that's what I explained last time. So I give you 4 examples last time, and we are going to have a lab this week regarding this point. So what we did here in this part, given a circuit, I didn't ask you to design the circuit. That's what I'm going to do today. So I just give you a circuit, okay? And then I'm asking you, can you obtain what we call a state diagram or a state table instead of truth table? Okay. So here, this is how you can describe, or how can you make a relation between input and output. Okay. So here, we have what we call a state table. As you know, in the state table, you have in this part here, you have the current. In this part here, you put all the states. This is the current state of the flip-flops you have. If you have 2 flip-flops, I'm going to put 2. This is the current value. This is the current X, the current input. Is that okay? And this is and this is the current Y, the current value for Y. And this is when the clock comes, given this is the input, this is the current value for the flip-flop. When the clock comes, this will be the next state. That is why we have states. What do you mean by state? A state means the values of the flip-flops. That's it. You got what I'm saying? So here we have state 0. So based on the value of the input, you can move from state 0, you can go to state 0, or you can go to state 1. Who's gonna dictate this? Who's gonna control? You are gonna go to this state, or that's the input. The input, based on the input here. Same thing here, you are in state 1, and you can go to state 0, or when the clock comes, that's why the transition at the clocks, as I said last time. Or you can go to state 1 based on the value of the input. Is that okay? And for every row here, you have some value for the output here. Is that okay? Also, I told you, and that's what you will see. Sometimes here, this is in general. Here I have only 1 input, but maybe in some circuits, I don't have any inputs, as you will see today. That's okay. It's okay. You're not going to have this column. That's okay. But you must have this part for sure, because if you don't have flip-flops, you don't have sequential circuit, okay? Here, because I have 2 flip-flops, I have 2 here. If you have only 1, it's going to become 1. If you have 3, it's going to become 3, and so on. Okay. We always have this one. Sometimes we have 1 output. Sometimes you have 2 outputs. Sometimes you don't have any outputs. You got what I'm saying? But how a circuit doesn't have output? Okay, I want to be precise here. In this, when I say we have output, I mean the output we are going to get from a combinational circuit, as we did here. Okay. So here, this output I'm going to get from the combination circuit. Sometimes, as you will see today, we don't have this output. So when I say we don't have output, usually what happens, I'm going to get the output from the state here. So my output is the states. You understand what I'm saying? But I don't want to call this one output, because I call it a state, and also I don't want to be confused with this one, the output you get from combinational circuit. Okay? So here, at least you are going to have states, at least, okay? At least you are going to have state here. This is a minimum, right? You may not have input, you may not have output. You may have 2 inputs, you may have 2 outputs. Is that okay? Because as I told you, for sequential circuit, you must have flip-flops. Once you have flip-flops, you have present state and next state. That's it. Okay? So I explained this one. We created what we call a state table, and then from the state table, we created what we call a state diagram. I was very clear last time, even it is written here, either a table or diagram, they give exactly same information. Same information. Is that okay? But maybe this one like in a visual way. This one in a visual way. I don't know why. Maybe a problem in the project. Yeah, this part is not shown. Okay. I can do that. Oh, yeah, right. Thanks. No. Oops. Okay, good. So is that okay? And by this way, if you have a state table, it's easy. It should be easy to go from state table to state diagram. If you have a state diagram, it should be easy to move from here to here because both of them have the same information. But I display it here in a table. I display it in a visual way. Okay. Any question? And you can see what I told you. You can see the behavior of the circuit here. If I'm in state 0, so if I give you this one, what do you understand? I understand very easy. If I'm in state 0, 0, if the flip-flops are 0, 0, okay, and then the input 0, input is 0, okay? When the clock comes, I'm going to stay here in this state. So next is going to be 0, 0, okay? And the output here is the output is 0. This is the output. But if x is 1, so here if I'm in this state and x is 1, so when the clock comes, I'm going to move to here and output is 0. So now you can get the relation between the states, input, and output. That's why I'm telling you this one should describe the behavior of the circuit. Okay, so I explained these 3 examples. This week we are going to do a lab on this part. Yeah, so here I'm going to move to the next section here. In this section, I'm going to talk about state reduction. So first of all, I'm going to tell you what we are going to do here in this section, similar to what we did in combinational, okay? So remember in combinational, when we have, for example, you have x, y, z, and then you have f1 and f2. You remember when I explained the term equivalent, when I tell you these 2 functions are equivalent, but maybe one of them more simplified than the other, but they are the same. That's what we did, right? So how I made this term, how I can say if the 2 functions are equivalent or not, how we did it in combinational, okay? Because that's what I'm going to try to do here in sequential. Okay? So what's going to happen here is, as I said before, you can just to compare the output here. If they are identical, in this case, I say these 2 functions or these 2 circuits are equivalent. Okay, equivalent means they are do the same thing. Okay, and based on what you learned key maps and also algebra manipulation to do reduction. So if I have a function, I can reduce it, and both of the same are equivalent. Is that okay? I wanna explain how can you do the same thing here in sequential circuits here. Okay. By the way, I see some students are busy learning some stuff related to the quiz. We may not have a quiz today, okay? Maybe I'm going to shift it to next week because I want to finish these 2 today, okay? So pay attention to me because this topic is important and a little bit tricky, okay? So anyway, let's start with the first one. Okay, so here, you see here, these two state diagram. Every state diagram is a circuit, as I said. So this is like a truth table, or this one is a circuit. It's a circuit, okay? Sequential circuit. This is another sequential circuit. You can look at both of them. You can see this one is more complicated than this one. You can see this one simplified. Is that okay? So that's what I'm going to teach you today. I'm going to teach you today. Sometimes if you have a circuit complicated like this one, okay, how can we simplify it this way? Okay, similar to what we did in the key maps, but here we're not going to do key maps. Here it's much easier than key maps. Okay, so this is number 1. Number 2, how I can know if these 2 are equivalent or not. Okay, so so here I'm going to make a new definition for equivalency here in sequential circuit. So let's look at the definition. Actually, 2 diagrams are equivalent. Okay, if for the same input. I'm going to get the same output, okay, regardless of the states. You may have different states because you can see here, we have here much more states than the states we have here. You got what I'm saying? So for example, here, if you apply this input to this circuit, this is the output I'm gonna get. Okay. If you apply this input to this circuit, this is the output I'm gonna get. Okay. If you look at these two outputs, they are the same. Okay. But there are several things here. Wait a second. How big is the input? Because you told us the input is only 1 bit. Yes, it is 1 bit, but it's like a sequence. It's a sequence. So look here. First of all, when the input is 0, I'm here in the beginning, I'm assuming I am at state A. So you are here at state A. Is that okay? And then I get sequential. So I get 0. Okay. So if I'm here at state A, and then the input was 0. So what is the output? So next state, I'm going to stay in A. As you see here, next state, I'm going to stay in A, and the output is 0. So that's why I got here 0. Okay. And then next time, next to clock, because everyone here related to clock. Next time, or next to clock, I got here 1. So here I'm in state A, and I got 1. State A, and I got 1. So what's going to happen? I'm going to go to B. So that's why you can see next one here is B. Okay. And then what is the output? The output is 0 here. So that's why I got 0 here. Okay. Let's now move to this one. Now I'm in state B here, state B, and I get 0. Okay. So if you are in state B and you got 0, if the input is 0, so you are going to go to state C. Next time you're going to go to state C, and also the output is 0. Is that okay or difficult? Should I give more examples? You got what I'm saying? So anyway, so if you continue this way and you do the same thing for this circuit, okay. So what I want to say here, for any sequence of the input, if you get, okay, so if you apply the same sequence of the input to the two circuits, if the two circuits are going to give you the same output, so I can say they are equivalent. They do the same thing. They are equivalent, right? Any question? No, there should be a question, because there is a tricky point here. How big is the sequence? What do you mean by sequence? Because it's a series. You got what I'm saying? This is the problem here, because you can have infinite number of input sequence, because it's a series this way. It's a sequence. You got what I'm saying? So that's why it may be difficult if I give you two circuits. This is different from combination. Combination is much easy. In case of combination, you have to calculate F1, F2, and then see if they are equivalent or not. So that's why here it may not be a straightforward, or just a definition, but it's going to be difficult to apply this definition to see if these two are equivalent or not. Okay, because you may have, unless you can limit, if you limit the size of the sequence, because you need to try all possible cases for this size. It's not only for one sequence. Okay, when I say equivalent, that means similar to combination. For any input, you get the same output. It's the same thing here for any sequence. Okay, so for example, if I say this is the sequence, you have to try all possible cases for this sequence. So that's what I want to say. Okay, so now I'm going to move to the next point. The next point is, okay, so now given this one, how I can do reduction to reach to this point, and this is very easy. Okay, so that's what I'm going to explain now. Again, what I did here, guys, is like a definition. How I can say two sequential circuits are equivalent. Okay, that means for any sequence, for any combination, for example, if I assume the sequence is 6 bits or 5 bits, for any combination here, you get the same result like this one. Okay, so that's why I can say it's equivalent. Okay, but what we're gonna do now, what we're gonna focus on now is we will take one circuit and see how can we do reduction to this one. Okay, I'm gonna tell you how. So, okay, so in order to do reduction, sometimes there are two states that are equivalent. So I need to look at the states that are equivalent, do the same thing. If I can find two states that are doing the same thing, I can just combine them together to one state. This is the main point. So, okay, so what do you mean by two states are doing the same thing? I'm going to tell you what I mean. For example, here, if you look at this is the table. For example, if you look here from here, it may be difficult, or it may be easier to work on the state table here to find the equivalent states than working on the graph. But still, you can figure it out from the graph. So look here. For example, if you look at state E and state G, look how they behave. Look how they behave. So if you are in state E, okay? And then you got 0. So you are gonna go to A and output is 0. So look at what about G? It's the same thing. So is that enough? No, you have to look at the other one as well. Look at the other one, okay? If you are in E and got 1, you are gonna go to F and also are gonna be output is 1. It's the same thing here. If I'm in G, okay, and then so both of them are gonna go to the same state, and also for the same input is gonna produce the same output. That's why I can say they are the same. So I can combine them together. Okay, but again, it may not be easy to get something like that from the table. From the diagrams. That's why I'm gonna get it from the table. But this is the concept. This is the main idea. So the main idea, in order to do reduction, you need to look for the states that are doing the same thing and then combine them together. How can you do that? It's easier from the table. So that's why I'm gonna go to the table here. And for example, here, if you look at this table here, I told you last time. Yeah, so yeah, this is the same table here. Last time I explained 2 ways to make this table. One of the ways, this is the second form I explained for this table. Every row here, it has, every state has 1 row, as you see here. So if you are in state A, okay, X is 0, you're gonna stay at A, and your output is 0. Because this X is 0, X is 0. But if you are in state A and X is 1, you are gonna go to state B here, and the output is 0. Okay. Anyway, so this is for every state has, for every state it has 1 row. Okay. This row is telling me what is the next state for the 2 inputs we have, and what is the output in the 2. So in other words, you can see here for every state we are gonna have 2 output here, 1 from here and 1 from here. These 2 output are actually represented here in the row, in this row. Okay. Anyway, so once you have this table, that's what I told you. Look now, I wanna find the states that are equivalent. How I can find them? So look here. So if you look at this state and this state, I can see they are doing the same thing. How? If you look at the rest here, they are exactly same thing. So this is A, F, 0, 0, 1, 1. So they are the same. Okay, and they are behaving the same. So that means if I'm at E and then X is 0, so I'm gonna move to A. In both cases we are gonna do the same thing. Okay, and they are gonna output zeros. Both cases will do the same thing. Okay, or if I'm in E and then X is 1, so this one is gonna go to F. This one also will go to F. Is that okay? And both cases you are gonna output 1. Okay, so let me see. So how can you identify them? Very trivial, very easy. So for example, is these 2 are equivalent? Let's see if the rest of items here are identical. The answer is yes. So if you look here, it is not okay, because this one will go to A, will go to C. So these 2 are not equivalent. Okay, so you can do this way. So by looking at the states here, I found these 2 states are equivalent. So in this case, I can merge them together. So in this case, I can cancel one of them. I just select G, you can select E, doesn't matter because they are the same. So I can merge. When I merge, you have to do 2 things when you merge. Okay, number 1, you need to cancel one of them. So I'm gonna cancel G. So now G is equal to E because I merges them together. Now I'm gonna cancel this record. Okay, and now number 2, you need to look here if anyone going to G, and you have to replace it by E because now E and G are the same thing. You got what I'm saying? So you have to do 2 things. Number 1, once you find 2 are identical, number 1, you need to remove one of them. This is number 1. And now because G is equal to E and there is no G anymore, so every time you find G in the table, you have to replace it with E. Is that okay? So now I made a reduction. What kind of reduction I made? Instead of having 1, 2, 3, 4, 5, 6, 7 states, okay? Now, if I have 7 states, now I have 6 states. Is that okay? This is the new table. So now I have, yeah, so here I'm moving for, yeah, this is the new table here with the 6 states. 1, 2, 3, 4, 5, 6. Okay. Is that done? Done or not? You need to think again. So now I was able to make 1 reduction from here to here. Okay. Now, and you see, I replaced this one from G to E, as I told you. Now, let's look for similar states again. Okay, and that's what I did here. So I'm gonna work on this one here. I found we have two states that are identical, G and F. So if you look here at G and F, you find this part here is identical to this part. That means they are equivalent, okay? So in this case, I can remove one of them. For example, I'm gonna remove F. I'm gonna remove F here, okay? And then because now F is equal to G. So every time you have F, you need to make it G. So here, if I look here, I found we have two F here. So I'm gonna make them G and G, okay? So now this is the new table. Yeah, this is the new table I have. Is that okay? And now, can you do more reduction? Let's see. Can you find any two states that have identical rows? If you can, so I can to reduce it more. Okay. So for example, if A and B, for example, you can see here they are different in the first one, so I don't need to continue. A and C, they are the same here, but they are different here. You don't need to continue. For A and G, they are different here. Okay. A and E, they are the same here, they are different here, so you don't need to continue, and so on. You got what I'm saying? You can't, I can't. Okay, there is a tricky point here. So what did you do so far? What I did is I was able to reduce the number of states from 7 to 5. That's what I did, right? Okay, so does that mean I can reduce the number of flip-flops I need? Because there is a relation between flip-flops, okay? Because this is the main point here. The main point, I wanna minimize the circuit so that I can use less hardware. You understand what I'm saying? Less hardware. So the question now, by doing that, do you guarantee that you are gonna reduce less hardware? The answer is sometimes yes, sometimes no. It's not guaranteed. Why? I'm gonna tell you why. Simply because if I have n flip-flops, that means I can have up to 2 to the power of n states. Okay. So for example, in this case, if you have 2 flip-flops, so you can have up to the power of 2, which is 4 states. Okay. So now if I need more than 4 states, for example, I need 5, 6, 7. Okay. So in this case, or 8. So in this case, you have to have 3, because three flip-flops is going to give you 2 to the power 3, which is 8 states. So in this case, although I reduced it from 7 to 5, but still I need 3 flip-flops. You got what I'm saying? Yes, 3 flip-flops is going to give me 80 states, but I'm not going to use all of them. I'm going to use up to 7. Here I use only 5. So that means after all of that, actually I didn't reduce the hardware. That's why I'm telling you, you still need to know this one. But I'm not gonna usually. It's not about me. Usually, when this topic in this course, usually we don't put so much focus on this one comparing to the key maps, because usually key maps make reduction. This one you need to learn it, but it may not be very useful. That's why many people may not even. Or it's okay. It's not that important topic, to be honest with you. But that's okay. This is something also you need to consider. But it's not guaranteed. That's what you should learn. Yes, I can reduce the number of states, but that doesn't mean doesn't guarantee that you are going to reduce the hardware you have. Any questions? Okay. Okay. So before I move to the last topic we have here, I want to summarize what I said here. Here I explained 2 things, guys. Number 1, how I can say definition, or how I can say the two state diagrams are equivalent. How I can say these 2 circuits, sequential circuit, are equivalent. Okay, similar to what I did in the combinational circuit. Is that okay? And then I told you for any combination, for a certain sequence, for any combination of ones and zeros, the 2 circuits should give you the same output, right? Also, I explained how can you do reduction, okay? How can you do reduction regarding the number of states, okay? So now you have 2 circuits, they are doing the same thing, but this one has 7 states, this one have 5 states, okay? Unfortunately, this reduction may not lead to reduction in the hardware. So that's what happened here. Yes, I reduced it from 7 to 5, but still I need 3 flip-flops. I was not able to reduce the number of flip-flops. You got what I'm saying? But still, I'm not saying all the time it's this way. I'm not saying all the time. Maybe if I was able to reduce it to 4, so this time, so now I reduced it from 7 to 5, but this didn't help me, because if you need 7 to 5 flip-flops, actually, states, you need 3 flip-flops. But if I was able to reduce from 7 to 4, yes, now I need only 2 flip-flops. You understand what I'm saying? That's why it does not always lead to any questions? Okay. Now, the last topic here, which is a very important topic, what I'm going to teach here, let me tell you what I did before and what I'm going to do here. What I did before is I give you a circuit, and yeah, so for example, here in this example, I give you already circuit. So I already designed the circuit. And then I asked you to give me the state diagram or state table. Is that okay? This is similar to combinational. If I give you, for example, here, it's similar to in combinational. For example, if you have already a circuit like this one here in combinational, so I already give you the circuit, okay? And then I ask you to give me the truth table. Is that okay? This is exactly equivalent to what we hear this one in combinational. Is that okay? So what we're gonna do in this section is the opposite, okay? So now, given the truth table, okay, or given the state diagram, how can you get the circuit? Is that okay? How can you design the sequential circuit given the state diagram? Okay, it's not actually given the state diagram. I'm gonna describe the problem to you, and then based on the description of the problem, okay, it's similar here in combinational. Usually, I don't give you the truth table. Usually, I give you a problem. I want to do multiplication. I want to do addition, and based on that, you create the truth table. And then from the truth table, you make the circuit. It's the same thing. I'm going to explain it now. Okay. So I'm going to make a description. I'm going to describe. I want a sequential circuit to do something. And then based on this description, it's easier to create the state diagram. Okay. Once you have the state diagram, you need to translate the state diagram to a circuit. That's what I'm going to explain now. Okay. So here, I'm teaching here 2 examples. This topic, for sure, it's a very important topic. That's why here I'm teaching 2 examples. And then, by the way, before I forget, to the end of the semester, we have 3 weeks, including 2 lab sessions. 2 lab sessions, okay? So we're not going to have more labs, okay? However, I'm going to, maybe today or tomorrow, I'm going to post the project, okay? So the project's like a lab, but like a big lab, okay? So the project will have 2 parts, okay? I wish you can finish the first part by next week, and then because we have only 2 sessions in the labs, okay? So for every lab session, you should finish 1 part, okay? And actually, these 2 parts in the project are actually just a twist. You have here 2 examples, 2 design examples for sequential. Is that okay? I just change them a little bit. So that's why if you understand this example, it should not be difficult to design, to do the project. You understand what I'm saying? I think because I think by these two examples, Zybox and also doing a project on how can you design sequential circuits, you should be okay. Okay. But anyway, so let's start. So here, yeah. So actually, to design a sequential circuit, you have to follow these steps. The first step is from the problem description, from the specification. So I'm going to give you a description. I'm going to tell you, I want to design a circuit to do whatever. So I'm going to describe to you words, okay? So based on these words, you need to create a state diagram. That's number 1. And usually this one is, again, I hate to say more difficult, but yeah, it's a difficult one. Yeah, sometimes this one needs to little bit to think about it, this part. But once you have the state diagram, these steps are systematic, just steps. Should be very straightforward. So from here, this part, maybe you need to think a little bit, but once you have the state diagram, everything after that is just straightforward, okay? So once I have a state diagram, number 2, you can look at the states and see if you can reduce the number of states, as I told you before. Number two, you can assign binary number for the states if you have not done that before, because usually what we do when I have a state diagram, I don't care about 0, 0, or what. I say just state 0. Then I'm gonna go to whatever state 1, and then I go to state 2, and then state 3. So I see how it works. I use just names: state 0, state 1, state 2, and so on. Okay, and then after that, for every state, I need to assign numbers, because this will be the number that flip-flop. So whatever you have here, the ones that you have to flip-flop. So in the beginning, you don't need to worry about what are the values. You just use state 1 and 0, and then after that, you assign binary number. I'm going to show you through 2 examples how can we do these steps. After that, once you have this one, you can have a state table using binary code, not states. Okay, binary code similar to the ones we have before. After that, you need to choose one type of flip-flops, so you can design the sequential circuit using D flip-flop, T flip-flop, or using JK flip-flop. You need to decide which flip-flop you want to use. In my opinion, I think D flip-flop is the easiest one. That's why in the project I ask you to use D flip-flop. It's easiest one. Okay, but anyway, sometimes T flip-flop is easier. I hate JK, but our JK is more complicated, I guess. Okay, JK is more complicated. I always, but sometimes T. I think most of the time T is easier. Sometimes, especially in counters, T because T has toggle. So sometimes this is the idea of doing easy toggles. You in T flip-flop, sometimes it's useful in case of counters. But anyway, you will see now. But you can design any circuit using any type of flip-flops, anyone. Is that okay? So you need to decide which one you have to use, and then from the state table, you need to get the input equation of the flip-flops. For example, if I have D flip-2, for example, I'm gonna DA equal, so this is the input of A flip-flop, for example, equal A or XB. For example, you need to find an equation like this one for the input. That's it. Once you do this one, you are done. So you will see right now an example, but I'm gonna repeat it again, guys. Listen to me. Again, the part that need to think a little bit or pay attention or be careful when you do it is actually how can you translate words to a diagram. Once you have a diagram, everything after that just systematic steps 1, 2, 3, 4. There is, once you know it, just you need to know how to. You don't need it's systematic. Any questions? So here I'm giving you 2 examples, and every example is a relay. I told you in the project we have two parts. Okay, part 1 is related to example number 2. That's why I'm gonna start with example number 2. Part 2 in the project is related to example 1. So I'm gonna delete this one. I'm gonna go to part 2, example 2 first, and then I'll go to example 1. Okay. So in example 2 here, I wanna design a 3-bit counter. Okay, a 3-bit counter. What this means? Very easy. It means you have here a sequential logic circuit. This sequential logic circuit has a clock. It has a clock this way. Is that okay? And now because this one is 3-bit, it has 3-bit output. 3-bit output this way. Is that okay? And then the output here is going to be a counter. It means number 1, this is the value of the counter here. It should be 0, 0, 0. When the clock comes, next time it becomes 1, then it becomes 2, becomes 3, becomes 4, 5, 6, 7, and then go to 0 again. Counter, it's counting. You got what I'm saying? So these are the flip-flops. I want to design a circuit to be something like that. Every clock is going to be transition from here to here, every clock. Someone can tell me why you made it like counterclockwise this way. Is that always? I don't think so. You can make it this way. It doesn't matter, right? But the textbook did it this way. I don't think it has. Is there a specific way to do it? You understand how the circuit works? Okay, so that's it. So I need to design this circuit. So every clock, the count incremented by 1. Once you go to 7, you go back to 0. Is that okay? Okay, so in this case, number 1, This is very easy state diagram, very easy. So here in this state diagram, as you see here, this is the states we have, okay? I need 3 flip-flops, okay? Because there is no input, because I didn't tell you there is input to do anything. Although I'm gonna modify after I finish, I can modify it to add an input, but forget it now. So this is simple one. I didn't tell you there is an input, okay? Just clock, okay? There is no output. Again, when I say no output, I mean there is no output coming from combinational circuit, but the output will come from flip-flops, right? So that's why this is my output, the flip-flops here. Is that okay? So that's why this one is very easy state diagram. I don't need to put numbers here as we did before, because always there is one transition. So remember what I did before. If the input is 1, you have to come here. But if it is 0, you have to go to here. This is not the case here. That's why this is very easy, right? This is not the case here. So all what you have to do is always, if you are in state this one, the clock comes just right here, regardless, because there is no input. Again, I can add input, but let's start with this simple case. So always, if you are here, next time this will be the next state. If you are here, this next state, next state, next state, next state, and so on. Is that okay? Any questions? So now with the state diagram, it's very easy. Okay. Any questions? Given this state diagram, how many, you need to ask yourself, how many, this is a very straightforward case or maybe easy, but usually, how many flip-flops do you need based on the number of states? In this case, I have 8 states, and you know there is a relation. So if you have 2 to the power of n flip-flops, give you the maximum number of states. So in this case, because I have 8, you have to start from, you should start from the state, okay? As you will, first you need to know how many states do you need in your circuit. That's number 1. And then you see, and then you need to decide how many flops I have to use to get this number of states. Is that okay? So in this case, because I have 8 states, I need 3 flip-flops. Is that okay? Any questions? Okay. After that, next step, once I have this one, and again, this is the most, it's not difficult here because this example is straightforward, okay? But you will see other example, maybe I'm gonna complicate it a little bit, but let's see. So this is the most important thing. If the circuit you are gonna design is gonna do this state diagram, is that okay? So, and this is systematic, easy way. Once you have this one, it's gonna easy. You can move forward easily. So, if this state diagram does not do exactly what you want to do, the circuit will not do exactly what you want to do, because the circuit will do what happens here in the state diagram. You understand what I'm saying? So the logic you have here, this is what the circuit will do. That's why if this one is not doing exactly the wording or exactly what you want to do, so the circuit will be different, a little bit different, okay? Or it's not the same. But here, yeah, this is straightforward. That's what I want to do. Every time here, 0, 0, clock, go to here. Clock, come 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 here. That's it. Straightforward, okay? Now, let's start with the next step you have to do. You have to translate this one from a diagram to a table, okay? So in this table, forget this part. This is not a part of the state table, okay? We're going to add it later. So in this table, I told you in the state table, you have here the current state, you have the next state. You have input, you have output. But in this case, we don't have input, we don't have output. Okay, so if I have input, I would put it here. If I have output, I put it here. So all what I have just states, okay? So in this case, I have, as you see here, that's what I have this part here, the current state. And when the clock comes, this will be the next state when the clock comes, okay? This is very easy, you can do it. Look here, this state is 0, 0, 0. Is that okay? When the state comes, it becomes 1. Yeah, because after 0, I want to get 1. Here, if the state is 1, when the clock comes, I'm going to go to 2. If it is 2, I'm going to go to 3. If it is 3, I'm going to go to 4. If it is 4, I'm going to go to 5. Okay, and so on. Here, if it is 6, I'm going to do 7. If it is 7, 7, 7, I'm going to go to 0. Make sense? Okay, so now once you have input and you have output, what should I do next? Very, very easy, very simple. What I do next is I need to find. Now I decided here in this example, as I said before, you can use any type of flips. That's why in the previous example, I'm gonna implement, just to show you, I'm gonna implement the same circuit using the three types of flip-flops we have. But for this one, I just selected one. Okay. Here I decided to use T flip-flop. Okay. I decided to use T flip-flop. Is that okay? Okay. In case of T flip-flop, you have only one input, T. Okay. So now, given this information, this is the input. This is the current state. When the clock comes, I want the flip-flop to move from here to here. So now what should be the input? Okay. Why should I put in the input so that if this is a current, everyone here is a flip-flop. Okay. So let's just, I want you to remember how T flip-flop works. In case of T flip-flop, if T is equal to 0, no change. That's okay. If T is equal to 1, toggle. That's how it works, right? This is the only two cases I have. Now, so given after you have the current state and next state, now I can get the inputs of the flip-flops. Okay, what inputs should be there? Okay, so let's see how I can make it. Okay, remember every one of these are flip-flops. Okay, so let's start, for example, with any one of them. So for example, here, this one is not here. Okay, I'm teaching now. After you have the present and next one, how can you fill up this part? Okay, so let's see how. Okay, so for example, I'm gonna look. I wanna design the input. I wanna look at the input of flip-flop number 0, E0. Okay, so look here. This one was 1, and then I wanna make it 0. Toggle. So in order to toggle, the input of this one has to be 1. Right? So in the current state of this flip-flop is 0, and then next time I want to make it 1, toggle, because it's toggle, so the input of this one has to be 1. Okay, I'm gonna continue this way. Look at the next one here. Now this one was 1, and then it became 0, so it's toggle. This one is 0, and then next time it has to be 1, toggle. Okay, this one is 1, and now it has to be 0. It is toggle. So if you continue this way, you can find all of them toggle. So now I finished E0. Okay, so now I know what is the input, what should be the input of this one. Okay, after that, I'm gonna move to the next one. For example, here, look at this one here, E1. If this is the current value for E1, when the clock comes, I want you to get 0. 0, get 0. That means no change. That's why the input here has to be 0. The next time, this one was 0, and then it has to be 1. So what should I put in the input to make this one happen? To make it happen, I have to toggle. I have to put here 1. 1, I got 1, no change, and so on. You got it? So now what you have to design, you have to look at every flip-flop. This is the current state for this flip-flop, and this is the next state. What should I put at the input here to get this value? To make this transition, to make the transition from 0 to here, for example, from 0 to 1. Or if you look at any other case, for example, this one was 0, the transition will be to 0. Okay, by this way, I can fill this one up here. So these are the inputs of the flip-flops that can move from this state to this state. Any questions? Okay, so what should you do next after that? Okay, after you do that, remember, this is it's like the input of now it became like a similar to what we did in case of combinational circuit. I have input, and then I have like function 1, I have function 2, function 3. Okay, so all what I want to do here, I want to get a relation between this one and this one. Okay, and I need to also to do simplification. So what I'm going to do, I'm going to take this one. Okay, and then as you see here, I'm going to have, these are inputs like X, Y, Z. So you can think this one like X, Y, and D. Then I'm going to make key maps, like this one is X, this one is Y, this one is Z, similar to what we did before. Okay, so it's like these inputs, and this is a function. I want to see which combinational circuit can give me these values. What combinational circuit is going to give me these values given these inputs? Okay. So what I did here, it's like I have three functions. Okay. One function, I'm going to put it at the input of this flip-flop. Another function, I'm going to put it at the input of E1. Another one, I'm going to put it at the input of E0. Okay. And then, as you see here, I just make simplification. I find here to get these values, the relation is from these values. So to get from here to here, the relation is actually E0 and E1. So if you end E0 and E1, I'm going to get this one. Is that okay? Then I'm going to repeat it again for this one. Okay. I find TE1, the input has to be equal to E0. So if you look here, this one is equal to E0. Is that right? Yeah, it is equal. So this one is equal to this one. Even if you can observe it, you do even if you have this observation, you might not even need to do the key maps. Because I'm saying, if you just look here, this one 0, 0, 1, 1, 0, 0, they are equivalent. So okay. Any questions? One more thing. Look here. Look here. Actually, here I don't even need to make a key map here. Why? Because this function f is equal to 1. It's all the time once. So anyway, so you don't even need to make a map here because f is 1. This one is 1 all the time. Is that okay? So now very simple. Now I have 3 flip-flops. Okay, I have 3 flip-flops. This results are telling me for the A0, the input here has to be 1 all the time, 1. For TA, for A1, the input here has to be A0. The output from here to here, A0. Okay. For number 2 here, the input here is actually A0, A1. That's it. So I'm done. We're done. So now, yeah. So now I have, as you see here, I have 3 flip-flops. This is A0. This is A1, A2. A0, it has 1 all the time. Okay. A1, for A1, as you see here, A1 is equal to A0. This is what I got from the result this here. Okay. And then the input here for this one is actually E0 and E1. E0 and E1. I am done. So this circuit should do same thing as we have in the state diagram. Okay. I'm gonna tell you like a trick. How this design, we already designed this circuit, we are done. But I'm gonna tell you a little bit trick, especially in counters, in case if you make a counter. Listen to me, okay? So what I'm saying here, if you look here, this one is 1. What it means when the input is 1, what it means? Every clock you toggle. That's what it means, right? This one here is coming from E0. What it means? It means when E0 is 0, this one is not gonna toggle. It's gonna be no change. But when the output here is 1, this one is gonna toggle. Okay. Again, okay. Look at this one. So what this one is telling me? This one is telling me this one will toggle when this one is 1 and this one is 1. This is how it is. But how, what you explained, I'm going to say it again before I tell you how it is related to counting. Okay, I'm going to tell you, but for now, I'm going to say the observation again. The observation is, I see. First one here is toggling all the time. Clock comes, toggle. So every clock it toggles. This one is going to only toggle when E0 is 1. This one is going to toggle when E0 and E1 is 1. Okay. This is actually the truth table you are doing. So if you make a truth table, if you make a truth table, guys, for example, you have here X, Y, Z. If you look at the first one here, 0, 0, this one should have like 0, 1, 0, 1, 0, 1, 0, 1. Is that right? So you have to toggle every clock. So if you want to make numbers, okay, so this one has to toggle every time. The second one here should be 2 zeros, 2 ones. Okay, so this, as you will see right now, this, because of this one here, this one is gonna make it toggle for 2 clocks. You will see right now. So to understand this observation, I made this diagram here. So if you look at this diagram, guys, here, this is how I'm gonna get numbers. If you look here, 0, 0, 0, this number 0, right? Here we have 1, 0, 0. This is number 1. Now we have 0, 1, okay, 0. So this is number 2. Then I have here 1, 1, 0. This is number 3. We have 0, 0. So every count is gonna stay for 1 clock. It's counting, but every count is gonna stay for 1 clock, okay, as you see here. So that's why if the clock is fast, counting will be fast. If the clock is slow, counting is gonna be slow. Okay. Anyway, so same thing. So here, if you, for example, if this is 4, if you see what happens here, this is 1, 0, 1, which is number 5, and then after that you see it is 0, 1, 1, which is number 6, and then you see here 1, 1, 1, which is number 7. And then after that, 0, because this one is going to go to 0, 0, 0, you are going to get 0, 0 again. Is that okay? It works. But now let's come back to my observation. My observation was, look here, the first one has to toggle every clock. Yeah, because if you look at the pattern here, the pattern we have is 0, 1, 0, 1, 0, 1. So that's why it has to toggle every clock. And this is what we got in the design. Okay? Look at the second one. In the second one here, actually, this one should only toggle when A0 is 1. And that's exactly what's happening here. If you look here, at this moment here, A0 is 1. That's why this one will toggle from 0 to high, right? And then I have to wait for another clock in order to toggle again. Okay, and then I have to wait for another when this one becomes 1 in order to toggle again. Okay, and so on. Okay, same thing. Look at the next one here. The next one, in the last one here, look, this one has to toggle when both of them are ones. Okay, so at this time they are gonna toggle, and also at this one they are gonna toggle. That's why I'm gonna get 4 zeros and then 4 ones here. Anyway, in other words, you can also have another observation here. Okay, you can have another observation. If you look at the frequency here, can you get some information here about the frequency? If this frequency is if this is, for example, if clock, what is the frequency here? If clock divided by 2. Is that okay? Because the time here is double. The time here, one cycle here is equivalent to 2 cycles here. Time is double, frequency is half. Okay. And then you can see this frequency, this is, for example, F1, or we call it F0. F1 is actually F0 divided by 2. Because, if you look here, the time here is actually double the time here. So this is, if this one is F, so this one is going to be divided by 2. And this one is going to be half this frequency. This one is going to be half this frequency. Is that okay, guys? Any questions? Okay, let me tell you something important because somehow it's related to the project. Okay, listen to me. Here, I created a counter. Can I change this design to make it for any sequence? The answer is for sure yes. For example, after 0, I want to get 1, 1, 0. Okay, you can. It doesn't need to be a count. I need a sequence, whatever the sequence is, counting or gray code or whatever. Okay. For example, after 1, 1, I'm gonna get, for example, 1, 1, 1. Any sequence. Yes, you can. So all what you have to do, you just modify these values, modify the table, modify here the input of the table here, these two, and then modify these ones, and then you can design it. So although here I made a certain, because counting 0, 1, 2, 3, 4 until 7, it's a sequence. I can make any other sequence. I can make 0, and then after 0, 7. After 0, 7, 3, whatever. I can make any other sequence. Is that okay? This is number 1. Number 2. Can I add? That's what I'm asking you to think about it. Can I add one input here? Can we add here one input? Another one input, so that this input can pose counting, or so currently we don't have any inputs. Is that okay? Can I add one input so that currently we have no input. That means once you run the circuit is gonna count. You have no control anything, just count. But I can add one input so that now it becomes, this is, you have here output, you have here clock, and then I can add X here. If X is 1, it's gonna count. If X is 0, you are gonna pause. Yes, I can. So, but how you will change it? Very simple. All what I have to do, again, this is the most important thing, guys. Whatever you have here, the circuit will do that. That's why this state diagram is very important. Okay. So now I'm going to modify it. How can you modify it? I'm going to tell you here, I'm going to say X is 1. When X is 1, please move from here to here. But if X is 0, please stay here. When X is 1, please come here. When X is 0, please stay here. So I can continue this way. So for any state, when X is 0, I'm going to stay in this state. When X is 1, I'm going to move to the next one. Okay. So once you modify this one, you need to modify this one. How? I'm going to add one input here for X. Here, one input for X. Is that okay? And then based on that, I'm going to, you don't need to change the next state. Oh, sorry, you need to change the next state because when X is 0, if you have 0, 0, 0, next state is 0, next state is gonna be 0, 0, 0. So you need to update the table here, okay? And then after that, you need to update these ones here. And now, these ones are gonna be function in present state and X as well. So you can see X here. Is that okay? By the way, this circuit, we have already done it before. So let me go back to show you where we did it, okay? If I go back, I think it was one of the example in the analysis. Yeah, this one here. Yeah, so we already did this one before. So here, this one is a counter. If it is 0, and then X is 0, so you are gonna stay here 0, don't change. If X is 1, so now you are gonna count 1, right? Then 2, 3. Then you go to 0, you continue this way, as long as X is 1. At any time when X is 0, you are gonna hold, you are gonna pause, you're gonna stay in this state. So we already did it before. Okay. Any questions? Okay. Now let's go to the first example here. So again, because this is a coming lab, project. 2 parts. One part is about how can you generate sequence and like a counter. So that's why I told you this one is very close to the example I explained now. The second one is actually second part of the lab is actually how can you detect the sequence. So if you have 2 different sequence input to the circuit has to tell you which sequence. So it's going to be like the opposite. So now I'm going to make a circuit that generates sequence here, for example, and that's what actually you are going to do here. I have one input. This input can be 0 or 1, the input here, but I'm not going to use it for both. So I'm going to use it to generate 2 different sequence. If it is 0, you are going to generate sequence 0. If it is 1, you are going to generate sequence 1. Is that okay? So either you generate sequence 0 or sequence 1. Okay. Then you have another circuit here. We call it a detector. So this circuit should receive a sequence, and based on this sequence, it has to decide if detector has to tell you what is this sequence. The sequence 1, have you detected sequence 1 or sequence 2? Got what I'm saying? So this will be the second part of the. I'm gonna make some videos. I just want to make it easy, but these 2 examples are very important. If you understand them, it should be easy to do the project. So let's explain here what we want to do. So here I want to do this is the description. Again, this is the description of the problem, guys. Okay. Again, the most difficult part is just how can you get this one here. That's it. If you can get this one, everything after that is systematic. Just repeat. But this is the most difficult part. Okay. That's what I'm going to explain now. So now look here. Yeah. So here I want to detect sequence, okay, of 3 or more consecutive ones. So as you see here, we have an input here only one input, and this input we have a sequence here. Okay, every time you detect 3 or more consecutive ones, you should output 1. Otherwise, you should output 0. Is that okay? So let's see how it works. For example, here, I'm gonna start to, or you can start. Yeah. So for example, look at this example here. For example, here in the beginning it is 0, so I have to output 0 because I did not detect 3 zeros or more. Is that okay? Now, next clock. Now, here I have only 1, right? So that's why the output is 0. I didn't detect three zeros or more. Okay. Now, if you look here, also I'm gonna output 0. But now, if you look what's gonna happen here, now I have 3 here. I was able to detect 3 once. So that's why I'm gonna output 1. Okay, what about here? What here? I detected more than 3 once. That's what I'm telling you. More than 3 once. That's why I'm gonna output 1. Here, I detected more than 3 consecutive ones. That's why I'm gonna output 1. Here, because the last 3 or at least more than 3 once, I output 1. But now, when you have 0 here, yeah, if you look at the last 3, they are not consecutive series. That's why I'm going to output 0. Same thing here. If you look at the last 3, okay, so as long as at least the last 3 are ones, okay, so that's why I'm going to output 0. It's going to stay all the way this. You understand how the circuit works? So you have sequential input, okay? So this is a description. Based on this is the difficult part. Based on this description, how can you make a state diagram? This is the difficult part. Once you know that, once you do the state diagram, everything after that systematic, similar to what I said. Okay. So let's explain how can we do it. Look here. Okay. I'm gonna move it. Let's think about it. Okay. Look here, guys. Let's see. Here in the very beginning, I'm gonna have a state. I'm gonna say state 0. In state 0, here I have 0 when I receive 0. So that means when I receive 0, when x is 0, okay, I should. So if again you have serial, you have serial input. If I now received 0, so I should be here in this state. So what I have in hand now is 0. Okay. So if you receive 0, and now you received another 0, I'm gonna stay in this state. So this state is telling me. I received 0. What I have in hand is 0. So I'm going to stay waiting here. Makes sense, right? Because I should start counting once I receive 1. Because we need to count for 3 once. Is that okay? So, okay. Now, as long as I'm receiving 0, 0, 0, 0, 0, I'm going to stay in this state. Okay. If you received 1, so I'm going to come to this state if I receive 1. Okay. Here is state 1. So state 1 means I have 1. I have in hand 1. Is that okay? I'm looking for at least 3, remember, but I have 1 in hand. Okay. Now let's look at the easy case, okay, first, or the straightforward case. Now, what happens if next one was 1? Okay, so here means I have 1 in hand. Okay, so I'm gonna go to state 2. State 2 means I have two ones. The last 2 were ones. Okay. Now, what if the next one is also 1? So that I'm going to go to state 3. And state 3 means I received 1, 1, 1. Is that okay? So state 3 here means I received at least 3 ones. I didn't finish, but let's think this way. So in the very beginning, if the last bit is 0, right? So I have to wait here. If it is 0, 0, 0, I have to wait here. Once I get 1, I'm gonna go to this state. So if I'm in state 1, it means I have only one in hand. I need to get 3. I need to count for 3. I need to find 3 consecutive. Okay. Assume the easy case. I got 1, 1, 1. The easy case. So once I got 1, I'm gonna come here. Once I come 1, I come here. So if I come here, that means the last 2 were ones to come here. Okay. If I come here and get another 1, so that means I will come here. So once I come to this state, that means I already received 3 ones. Let's complete. I didn't complete it. Let's complete now. Look here. Okay, so here in state 1, if you receive 1, you are going to move from here to it. What happens after 1? I got 0. So this 1 bring me to here. But after that, I get 0. What should I do? Yes, I have to go back here to this state again, because this state means I have 0. So I have to look for another 1, because I'm looking for 1, 1, 1. Make sense? So yeah. So now, because you need to consider the two cases, if x is 1 or x is 0. So now if x is 0, I have to come back to here to look for another 1, because I'm looking for 1, 1, 1. Okay. Now, what if when you come here, that means you received 1, 1. Okay. After that, I may get 1 or I may get 0. If I get 1, so I'm going to move to here. I'm done with this one. What if you get 0? So after 1, 1, I got 0. What should I do? So I have to go back to here again if you get 0. Because you need to look for another, another sequence. I got 1, 1, 0. So I need to go back again to look for 1, 1, 1, 1. Make sense? Let me finish. Then once I come to here, I already have 1, 1, 1. Okay. What if after 1, 1, 1, there are two cases? I already have 1, 1, 1. There are two cases. I may get 0 or I may get 1. Okay. If you get 0, that means I have to go back to here to look for another sequence. So here, if you get 0, if I get 0, I have to come here. But the output here has to be 1. Because this is a purpose. The purpose of this circuit is the output has to be 1 when I detect, when I find the sequence. Everyone here the output is 0, because I did not detect the sequence yet. Also here the output is 0. 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 The only way to get output of 1 if I'm here in this state. Okay. So if I 1, 1, 1 and then I got 0, so I'm going to move to here to look for another sequence. And then this one is 1. What if it is 1, 1, 1, and then I got another 1? So I have to loop back to here. Okay. So if it is 1, input is 1, and then the output has to be 1. Yeah, so this is how it should look like. Sorry. Okay, let me explain it in a different way. Look here, guys. If you are in this state, that means the last bit was 0. Okay, last bit was 0. If I'm in this state, that means the last bit was 1. If I'm in this state, that means the last 2 bits are 1 and 1. If I'm in this state, the last 3 bits was 1, 1, 1. Okay, so as you see here, if it is 0 and then I got 0, so I have to wait here, because I'm gonna start counting when I receive 1. So as long as I receive 0, 0, 0, 0, 0, I'm gonna stay here. Once I get 1, the first 1, I'm gonna move from here to here. I think I have okay, so I'm gonna move from here to here. Okay, when I come here, that means I have 1 in hand. Okay. After 1, I got 0, so I have to go back here, because I need to look for, I'm looking for 1, 1, 1. So if I got 0, so already you damage the sequence. I have to start again, over again. So I have to go back, start over again. And then here, if I get 1, so I'm gonna come to this state. In order to come to this state, you actually need 2 1s to come here. Okay. After I get 2 1s, I get 0. So I'm gonna go back here, because you broke the sequence. I was looking for 1, 1, 1, 1, 3 1s. So I got 0, 1, 1, 0. So I have to go back again to count again from the beginning again. Okay. But if you get another 1, that means if you are in this state, that means you reset to 1, 1, 1. Okay. Once you reset to 1, 1, 1, okay. After 1, 1, 1, and you get 0, so I'm gonna go to the beginning again. Okay. But if I get 1, if I keep 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, so I'm gonna keep staying in this state. Okay. And the output here is 1. And if you are in any other state, the output is 0. Yes. Okay. Again, this is the difficult part. Once you have this one, everything else is going to be straightforward, similar to what I explained. Okay. So here I made this slide just to this is exactly what I explained. If the input is 0, you are here. If after 0 I get 1, so you are going to move from this state to this state. If you get another 1, you are going to move to here. Okay, if you then you get 0, I'm gonna move from here to here. Okay, so this is exactly what I explained. Any questions? Again, this is a difficult part. Now, after I created this state diagram, okay, it's easy to create the state table this way. Okay, so here I created the state table as you see here, but without numbers. I didn't put any binary numbers yet. Okay, I just see here, if you are in state 0, as you see here, x is 0, you are going to stay in state 0, and the output is 0. This is exactly, if you are in state 0, okay, you received 0, you are going to stay here, and the output is 0. Okay, so same thing here. If you are in state 0 and then you move to state 1, if you receive x is 1, you are going to move to here, state 1, and the output is still 0. The only way to get 1 in the output is when you are in state 3. Okay, so again, once you have this one, it's very trivial to move to this one. Okay, now you can look at reduction. Can I do any reduction here? Can you see any rows that are identical? You can't, right? So because if you see here, this one here, you are going to move S0, S0. So all of them are the same here. So this one is okay. But if you look at the next one here, you have 1, 2, 3. Okay, that means these are different. These two records are different. Look at this one. Maybe I can find some reduction here. Okay, so these are the same. These are the same. These are the same, but this is different. So no reduction. I can't do more reduction. Is that okay? Next step. All what I have to do, just now replace states by numbers. That's it. So in state, the way I'm going to do it here, as you see. Yeah. So here I decided you can put any number. It doesn't matter. Okay. Because the output of the circuit is not coming from the states. The output of the circuit coming from Y. You know what I'm saying? So here I decided for state 0, I'm going to put 0, 0. State 1, I'm going to put 0, 1. State 2, I'm going to put 2. State 3, I'm going to put 3. That's it. But you can put any number. It doesn't matter. Because this states, the output is not coming from the states. These states are just helping me to calculate the output. So you can put any numbers. It's not going to make a difference. Okay. And then by this way, I created this table this way. So this table, the only difference again, here in this table, every 2 rows are represented to 1 row here. So every 2 rows is represented to 1 state. So if you look here, if you are in state 0, 0, which is the first state here, so I call this one 0, 0, okay? And then x is 0. So you are going to stay in 0, 0. You are going to stay in 0, 0. And y is 0. But if I'm in 0, 0, and x is 1, so I'm going to move to state 1. This transition from here to here. And the output is 0. Okay? Okay, now once you have this table, once I have this table, I want to design using the 3 flip-flops. Okay, for sure any one of them should work, but I just want to tell you I can design by any one of them, and you can see which one is more complex than the others. Okay, so for example, I'm going to start with the D flip-flop. The D flip-flop is very easy. This is the easiest one. You know why the easiest one? Because unlike if I go back here to my example, look here, guys. Here for this one here, to create the input of T flip-flop, I have to make a new record. But if I use D flip-flop, actually I don't need to create a new record because D flip-flop is equal to this one. If I want to get these values, next time, so this should be the input of the flip-flop. So I don't need to calculate the input of the flip-flop because the input are equal to the output. You got what I'm saying? That's why this is the easiest one. Yeah. So here, so this one here is actually, don't be confused. This is the next state. So this one is actually equivalent to D of A. This one is equivalent to D of B. This is the input of register A. This is the input of register B. Is that okay? And then after that, this is the input you have. After that, I'm gonna use key maps. As you see here, key maps. So in key maps, you have this one like X before Y, this one like Z. You remember X, Y, Z? So this is X, Y, Z, as we did before. So anyway, so now I can take this one, I can summarize it, and then I get the input of this flip-flop. This input is function of these 3 values here. Then I can do B, and then I can do the output as well. Same thing for the output. So here it's like you have F1, F2, F3, just give me 1 minute to finish just this example. If you have F1, F2, F3 this way, and you have X, Y, Z, similar to what we did before. Assume this function, and then I got 3 values. That's it. Once you get the 3 values here, yeah, I just design the circuit this way. So once I know Y is equal AB, DA is equal AX or BX, this one is equal AX or B prime X. Okay, so now I need 2 flip-flops. This is the output of the first one is A, the output of the next one is B. Is that okay? And here, this is the D of A. I need this circuit here. You have input X. Okay, this is here for Y. Y is coming from A and B. Okay, same thing. This input here is coming from. That's I'm done. Is that okay? Next time, I'm gonna explain it again next time. So here, you can, here I'm teaching how can you do the same thing using JK and then using T flip-flop. I'm gonna explain it next time, just very easy. Again, the most difficult part is how can you create the state diagram that can do exactly what you wanna do. After that, everything is just systematic. You need to understand how this, you need to understand how the state diagram is working, at least so that you can verify, is this state diagram will do exactly what I wanna do or not? You got what I'm saying? Anyway, thanks.